So today we're going to do the GC analysis of the substitution products, the chloride and bromide from the N-butyl and T-butyl reaction. So the first thing we need to do is set up the GCs, which involves the instrument here, controlled by the computer with a little digitizer box and a hydrogen-air flame in our flame ionization detector. So inside the oven, you'll see there's a column here, and you may or may not be able to read that says this is an RTX5 column, 15 meters long, 25 millimeter diameter, and or 0.25 millimeter inner diameter, and 0.25 micron film thickness. And that gives a catalog number and a serial number on there. This is by Restec Corporation. So this is the column, and the information is on here again. RTX5 means it's cross-bonded 5% diphenyl, 95% dimethyl polysiloxane. And like I said, it's 15 millimeter inner diameter, 0.25 micrometer film thickness, 15 meter long rather, 0.25 millimeter inner diameter, and 0.25 micron thickness. So that's the column we're going to be using. And the other one seems to be missing. So I'll show you what the column looks like. Oops. Find one that's actually there. All right. So this is the column. It's just a glass capillary that's drawn out, 15 meter long, and spun. And then the end has a tiny little hole, 0.25 millimeter in diameter. And that's hooked up to our injector port and our detector. And when it's not in use, we push the end of the glass into a little septum like that so that it doesn't get contaminated. So I'll put that oven door back on. So before we turn the instrument on, we want to hook up the gases. The orange is for the hydrogen, and it's just a little quick connect. They're all different, so you can't accidentally hook up the wrong gas to the wrong location. Right. Especially don't want hydrogen being put somewhere where hydrogen doesn't belong. This one that doesn't have any color is for the helium. That's the carrier gas that we're going to be running through the column. And then the blue one is for the air, which is the other component of the flame. So those are all hooked up. And then we want to turn on the gas on each gas cylinder. And for the helium, we want to put that up to about 80 psi by turning this knob. And then we open up the hydrogen. And for the hydrogen, we hook that up to 60 psi. A little knob there. And then we turn on the air. And that also goes up to about 60 psi. So we open up the needle valve, so we have air flowing. And helium and hydrogen, and then we will open up these valves, these little ball valves, so we actually have gas flowing to the instrument. And what you'll see is up here we have air that's set at 50 psi, we have hydrogen that's set at 60 psi, we have a carrier P1, which is our makeup gas, that should be at 50, and then right now we're running at 120 kilopascals. And this is kilopascals here. All of these are in kPa, kilopascals. And this is set at 120 at the moment. The other thing we need to adjust is we need to adjust this split. And unlike the gas chromatography mass spectrometer, here we can't put the split number in digitally with the program, because this instrument is a little less sophisticated. So we have to know how far open the split is. So I'm going to shut that split down all the way closed. And I know for this analysis, I want the split open 6 full turns. So I'm going to turn it 1, 2, 3, 4, 5, 6 full turns open. Now I can turn the instrument on. I can turn the heater, right? That's going to heat the oven. I'm going to turn on the little digitizer. And then I can log into this computer. And the password is chemistry1114. And I'm going to go ahead and do the same thing on the other instrument. Just verify, right? We're at 50 kilopascals for air, 60 kilopascals for hydrogen, 50 for the makeup, and then the carrier. This one's set at 90. I can't remember what the carrier wants to be set at for this particular analysis. I'm going to have to look that up. But I do want to close the split all the way and then open it up 6 turns. And then I'm going to turn the instrument on and the heater and the digitizer and log into the computer. This one doesn't want to come back. I'm not sure what's going on with that computer. We'll come back to that in a minute. Windows is installing updates as always. So the program we want to open is called GC Real-Time Analysis. You see GC Real-Time Analysis, it looks like a chromatogram, and then the post-run analysis is the one with the magnifying glass. We'll need that as well. So I'm going to open up that program, accept all its little default messages, and sometimes it needs to be opened twice before the program will actually open. There we go. Now it's connecting the GC instrument, and if I watch this, it will eventually tell me that the link is okay, which means it's actually successfully recognized the instrument. So right now it's not ready, so I need to click this little thing that says System On, and that'll open up. And I'm going to cancel downloading the instrument parameters because I have no idea what the last person was running on this. So I'm going to cancel that. So now the system is on, and I'll move that over there. This will give me my injector and column and detector temperatures eventually. So I want to use the Select Project button here, and I'm going to go to the student drive. Right now it's pointing at the local disk, but I want to go to the student drive, where it says data, and there's a GC folder, and inside that GC folder there are some methods for chemistry 260. So I'm going to open that up, and I've got all the various methods. So this is instrument 2, so I'm going to open up the N-butyl halides 2 gas chromatography method. .gcm stands for gas chromatography method. And you'll see up here at the top it says N-butyl halides 2. .gcm is now open. And now I can send the instrument parameters by download parameters, and that'll send those over so it'll raise those temperatures appropriately. The injection port is here. It'll heat that probably up to about 250. And the detector is in here. This little cap. You see this little hole on it. This is where the hydrogen and air go. It's called a flame ionization detector. So what it will do is burn the sample in an oxidizing flame. In a reducing flame, right, which will add electrons to it. So we'll get negatively charged ions. Would be basically have a little nozzle, and in that nozzle we're pumping a bunch of electrons. So the ions or the molecules as they come through and are burned will create ions, negatively charged ions, and then there's a little collar that goes around the flame that they crash into to generate an electrical signal, which is then digitized in this little communications bus module and sent to the computer. So I'm going to need to light that detector, and we usually want to wait until the temperature of the detector is up around 100 before we light it. Right now it's at 83.2. And the way to tell it's lit is to hold the little watch glass behind the hole and see if you get condensation on there. If you get condensation, then that's an indication that the detector is properly lit. So now it's at 101. I'm going to press this button in. That will temporarily reduce the air pressure so it's mostly hydrogen. And you'll hear a little pop. Don't know if it was audible. And then if I hold that back there, you'll see that there's condensation coming on the watch glass. So that flame ionization detector is lit. And we're just going to wait for this thing to get up to an injection port temperature of 150 and a detector temperature of 200 and a column temperature of 65. So that instrument is ready to go. And this computer looks like it is having a hard day today. I'll have to turn it off and turn it back on again. Let that thing start back up. And while we're waiting for that, I'm going to go and find out what we wanted our pressures to be. So I'm going to open up the post-run analysis program. And I'm going to point that to my 2020 Fall Lab folder, so it'll be ready when we need it. And I'm going to go to Open, and I'm going to look for a file from last year that has that substitution data in there. So Davis Graham was a student last year, first semester. One of these is probably the GC data file from that lab, October 25th. That seems like a reasonable time. So let's see what he got there. So this is the T-butyl, and it says the carrier gas pressure was at 90 kilopascals. And if I go and open up his N-butyl, and looks like that's also T-butyl. Oops, wrong one. So maybe this one is the N-butyl case. Yep, that's the N-butyl bromide, and the carrier gas pressure is supposed to be 90 kilopascals, which I thought was the case. So we will go ahead and open or lower this carrier gas pressure using the carrier P2 over here, so that it's at appropriate 90 kilopascals. The combination of this pressure that we set here at 90 kilopascals and the degree to which this split valve is open controls the flow rate, how many milliliters per minute of helium is going through the column, which in turn affects the retention times. The other thing that affects the retention times is the column temperature. So you'll look here, this is where we also can tell that the column is an RTX5. ResTech is the company that we bought it from. The 5 stands for 5% diphenyl, and the rest, the 95%, is dimethyl polysiloxane, 15 meter long, 0.25 millimeter inner diameter, 0.25 micron film thickness. And then we're starting with an injector temperature of 150. We're running a column at 65 degrees, holding for 2 minutes. It's a very short run. And then our detector is at 200. And the range 2 here means that we're only taking 1 over 100. So it's 10 to the minus 2. We're multiplying the sample by 10 to the minus 2 in order to get it on scale. So this instrument is getting close to ready. This one was already at about 90 kilopascals. I just had to lower it just a little bit. And now we can log into this computer and get it going. And get our detector lit. It's usually a good idea to let these equilibrate for about half an hour before you actually come to run them. So normally that would be being done for you during the noon hour before your lab. I'm going to open up the real-time analysis program. OK that. Answer its messages. It's connecting the GC instrument. We'll hear it beep. And it'll come up here and say link OK when it's actually succeeded in connecting. That little chime that you heard is the indication that the instrument is connected properly. This is instrument number 1, or also Leonardo. Instrument number 2 here is Raphael, and then over here we have Michelangelo and Donatello, instruments 3 and 4. So we can always know which instrument we used. So I'm going to hit